So our first presentation for this session is by Minyoung Kim. Minyoung Kim is a senior research engineer at the Panasonic Silicon Valley laboratory. She works on deep learning projects for advanced driver assistance systems, such as real-time object detection and tracking. On those projects, she trains deep neural networks, implements new algorithms, builds optimized systems, and researches new technologies. Minyoung received her master's degree in computer science, specializing in artificial intelligence from Stanford University. And today, the title of her presentation is A Fast Object Detector for ADAS Using Deep Learning. I think we're presenting this one from the back of the room, so over to you.
Thank you very much. Hello, my name is Minyoung Kim, and today I am going to talk about fast object detection system that we had built in the past, and then especially for the ADAS using deep learning. So far, there has been a trade-off between using deep learning algorithm onto such a small, low-power device and achieving high performance, especially in the speed of the system. So I'm going to explain, okay, why is it so hard to achieve high speed at the same time achieving the high performance, and then and then later on, I will explain how we improved the such difficulties, and then for the last, I'm going to explain more about more recent activities in PSVL that we are working on. So before that, let me introduce about our team briefly. We are located in Cupertino, right next to the new Apple headquarters. And then we're about 20 people working not only in deep learning, but also in many other areas like design, control, robots, and drones, etc. So let's move on. Object detection system using deep learning. These days, many people know that the deep learning-based system has beaten state-of-the-art records in many domains, like computer vision, and in computer vision, image classification and detection, and then not only computer vision, but also in natural language processing, etc. However, there comes a downside too. So first of all, to achieve the highly accurate model training out of deep learning algorithm, you need large set of data, meaning you need a lot of data with the labels if you want to do the supervised learning. And then we know that it's kind of hard to gain the large amount of labeled data. And also, deep neural networks tends to have millions of parameters to be trained, meaning you need high computational power to even run the single for the propagation of the deep neural network. And since then, this kind of tends to be slower in the running time than most of the conventional algorithms like SVM, etc. So I think the main trade-off between using deep learning for the object detection system is speed versus accuracy. So it's kind of easy to, it got easier to build a highly accurate system when you use deep neural network for the computer vision task like the object detection system. However, it's not guaranteeing that you're going to achieve the high speed. On the other hand, if you want to achieve higher speed by sacrificing the accuracies, you can just build shallower network. But it still doesn't guarantee that you're going to get the both. So how can we catch these two birds in one stone? So to figure out how we can improve both of the properties, we need to first know how can we build the object detection system by using deep learning. So to build the object detection system, you need a classification network, meaning the classifier, it's called recognition network. So for example, we started to work on the object detection system from pedestrian detection, which was the binary classifier. So we trained very deep neural network for recognizing the pedestrian out of the background. So we trained very deep neural network to achieve the high accuracy on the pedestrian recognition. And then once you have this recognition network, then you need to run this recognition network on the images. But you don't want to run it on every corner, every pixel of the images because it's too much overhead. So you need to know that the filter, some filter, you need some kind of filters that filters out the unnecessary, the background images, or even the objects that you don't care. So that's how the proposal generation step actually does the job for you. And then there are some algorithms like selective search and edge boxes, which were widely used for generating the proposals, bounding box proposals for the detection. Generally, you can, by using these two algorithms, you can generate like 1,000 to 2,000 bounding boxes. And then once you have these candidate boxes, you run the recognition network to every boxes. And then finally, you can get the bounding boxes around the interesting objects. But then it's not the end. Like you don't need multiple boxes around the same objects, right? So there's an algorithm called like a non-maximum suppression that you can run, and then you can merge the bounding boxes nearby so that you can only keep one boxes per object. So this is how generally you can build the object detection system by using deep learning. And let's take more deep look at the object proposal generation step and also different scaling problem. So region proposal, when you use selective search, it takes 2 seconds per image when you use CPU. Well, it's like a little order of magnitude slower than the single for the propagation of the network. And then scaling, meaning if you want to have a more accurate bounding boxes, many people try this way, like you are scaling the images in various scale, and then you just run them multiple times for the propagation of the detection, or you just run the region proposal algorithms on multiple scaled images. But these are all time consuming when you compare the recent evolve of the deep neural network, because if you run the deep neural networks on GPU, it's much, much faster. It's like, I say like 0.1 seconds, but depending on the latest GPU, it's even a lot faster. So basically, these region proposal step and scaling are becoming the bottleneck of the whole system. So back then, it was in 2015, and then we tried to remove those to make the system faster. So we didn't want this region proposal step at all, and then we didn't want the scaling, because they're all bottlenecks of the system. So what we wanted to make the system is, we called it neural detector, and then this is the end-to-end trainable neural network. And then you just push the image, and then you just get the bounding boxes as an output of the neural network. So with a single forward propagation, well, there's another step afterward, meaning like merging the boxes. But generally, you can train everything inside one single neural network to get the bounding boxes as an output. So let me explain how we built it. So the recognition part was the same. So we trained a very deep neural network which recognized the pedestrian, and then we convert this recognition network to fully convolutional network, which became Detector. So back then, there was no like fully convolutional network, and then everybody was using fully connected layer at the end to get the higher accuracy. And then you can convert this recognition network to fully convolutional network, and you can take some advantages out of it. First of all, not only having just one single probability of being certain object, you now get the feature map on every corner of the images. So, for example, the red features on the right, the figures are showing, oh, there are some interesting features going on, which is probably the pedestrian. So you can take advantage of using these kind of features. And then what you do is that after you convert this network, you can add some regression layer. So what this regression layer does is that it actually tries to predict the bounding box coordinate directly. So you don't need any proposal steps. You don't need any candidate boxes. By just using single forward propagation, you are predicting the boxes directly. It gives you a lot fewer number of computation once you achieve the high accuracies. And by adding this regression layer, and then you can train end-to-end, now finally you get the detector network, which gives you the bounding box coordinates around the pedestrians by the single forward propagation. So this is how we built the recognition network. Back then, we were very inspired by Google Net, and we were using inception models. So we ended up having like 25 to 30 convolutional layers, and then we trained this network on Caltech pedestrian dataset. And this is the important part. Like from the recognition network, it had two fully connected layers. And when you have fully connected layer in the network, it produces a lot more number of parameters than the fully convolutional network. So this can be like increasing the size of your model. Now we didn't want to do that because we wanted to, and eventually we wanted to deploy this to the low power device. So how you convert this fully connected layer to fully convolutional layer? You can reshape, you train the network first, and you can reshape these parameters to fit to a certain size of the kernels. So you use certain size of the kernels on the followed convolutional layer, and then you can just replace whole fully connected layer. And then one major advantage by doing that is now your input size is not limited anymore. You can push not only just patches, you can push any size of the images, then you can get a different dimension of the feature map at the end. And this is another important part of the network. So regression layer, where we can regress the bounding boxes on the useful features. So when you looked at the feature map in previous slides, let's see here. Here, we don't want to predict the bounding boxes in every feature point. So this feature map has very low dimension compared to the original image, but we didn't want to predict all the bounding boxes all over the feature map. We only wanted to predict the bounding boxes on the activated area, which is red here. So this actually reduced the number of computations and also the parameters too. And then since making the training model conversion is very hard to directly produce certain type of numbers, so you need certain kind of techniques. So one of the techniques that works well is the normalization. So you normalize all the bounding box coordinates, and then you are you recalculate the bounding boxes within a certain size of the windows. We chose 240 by 240. And then now you have relative bounding boxes inside the window. And then you want to predict these bounding boxes coordinates. And then after you get the number, you can easily project back to the original space. So in some, to train the whole detection network is that you use the original image resolution, which was VGA scale in case of the Caltech pedestrian detection. And then you have fully convolutional network, which was converted from the recognition network, and then followed by the regression layers. And then as an output, you get the feature map plus the bounding box coordinates. And then to train this network well, we incorporated several loss functions. For the feature map, we used cross entropy loss, and then for the regression part, we used the Euclidean loss. So we built our own custom loss functions, which can combine to make the feature map training and the regression training works well. So this is a sample result of our detector. And then we trained on the Caltech data set first. And then we also augmented data collected from our headquarters in Japan. So this is the sample image of the Japan. I think it's the Panasonic. So these are sample results. The red rectangle's bottom shows the ground truth, and then yellow boxes on top was the detector. But there's a problem too we encountered when we had this detector. When you take a look, it looks like works well, right? But however, when you try to train the model which predicts the bounding box directly, the most of the problem that you encounter is the localization error. Localization error meaning even if it looks like working well, but when you want to evaluate on the ground truth box tends to be tighter than the boxes that you generate out of the detector. And then when you evaluate, you do the IOU, meaning intersection over the union, and then it turns out that you get a lot of errors actually. So for example, the bounding boxes for the second left pedestrian, it looks bigger. And then the ground truth actually is kind of tighter. So this results some problem, especially when the pedestrians are nearby. So feature map does not know if there's like multiple pedestrians or single pedestrian in one area of the features. So this results in like bounding boxes, one bounding box for the several multiple pedestrians. So to resolve these issues, we were thinking, oh, then what if we can train some features only on the center line of the pedestrian? So something like this. So now you can actually train the features only be activated on the center of the center position of the objects. Especially for this case is pedestrian. By doing this, now you know that like each pixel on the feature map represents certain size of the windows on the original images. For example, this is 120 by 120 windows that you're taking care of. Each feature map point takes care of. And then you can actually separate the multiple persons by using these features where the pedestrians are nearby but not too close by. So when you look at the third column of the results, there are some tiny pedestrians, then there are 2 to 3 pedestrians. Now you would have just a single box out of it if you just use the feature map and then directly try to predict the bounding boxes. But it doesn't work well because the regression layer gets confused. It doesn't know which pedestrian it has to focus on to predict the correct bounding box. But when you use these center height features, you now know that, oh, these vertical lines, you can say that, oh, these are the same pedestrian. It's working on the multiple object detection too, because you can stack each layer for doing the same job. And then you can separate each object from the feature map. So this actually improved a lot of the performances in the sense of the localization error. So this is a bit old results evaluation. We did an evaluation on our detector comparing the other method, and then this deep cascade paper was, it came out in 2015. That's when we evaluated our system. And then we realized that our system actually was maintaining the similar accuracy. However, our system was a lot faster than the others because we don't do region proposal and then we don't do any scaling. And then when we tested our system on the Titan X, it's the old Titan X, we could achieve almost 85 frames per second when we also used the DNN4. And then now we had a fast detection system. So we wanted to put this onto embedded device like Nexus 9. Nexus 9 is a tablet which has the NVIDIA Tegra K1. And then it only has like 192 CUDA cores. When you think about GTX 770, it has 8 times more CUDA cores than the tablet. So this tablet has very limited computational power. And then we still were able to achieve like 16 frames per second in a lower resolution. So this is the application we built. There's a threshold bar on the bottom you can adjust the threshold of the probability of the features and also the non-maximum suppression ratio because you still predict the bounding boxes along with your center. So you're predicting multiple boxes for the same person. So you need to merge these boxes. And then these are some sample results of the detection. As you can see, the bounding boxes are kind of having some errors on the localization still because this is the version using the lower resolution. So when you use the low resolution images, it's not only the computational power limitation, but also the output feature map, the dimension of the feature map that you get is very small. So let's say you used to have like 31 by 41 when you use the VGA scale. Now you just get like 10 by like 20 or something. And then and then that's why you can have the incorrect bounding boxes nearby. And then we took this detection system on one of the cluster, which had a Titan X, and then you can see that the localization error and then detection performance is a lot better in here. So this detection system we also demonstrated in ITSWC 2015, and now this system is being ready for the production. So we demonstrated on the laptop, which has the GTX 980M. Also, we demonstrated the tablets, which had the Tegra K1. And then later on, after like 2015, there has been a lot of works to achieve higher performance, both speed and accuracy on the object detection system. One of the most famous algorithms was FSR-CNN, which came up in 2015. And then they also agreed on what we thought, that the region proposal step takes a lot of time. So they wanted to also put these things into the training, end-to-end training. So they introduced the region proposal network, which can be run in additional 10 milliseconds, which is quite fast compared to the selective search. And then they tried to generate the anchor boxes to predict the offsets and the confidence out of it. And then after FSR-CNN, there has been another algorithm called YOLO in 2016. And then YOLO took more similar approaches as us in that they used fully convolutional network. And then they also tried to train the regression layers to directly predict the bounding boxes. However, the first version of the YOLO, they still had a fully connected layer right before the regression layer, which actually results in lots of parameters. So in 2017, I think they're going to present it in next CVPL. They improved the localization error. Since they used the regression technique as us, they also had the same issue, which was the localization error. So they also tried to improve these errors by incorporating the faster CNN stuff. They also tried to train the anchors boxes to make the regression layer trained easier. And then they eventually removed fully connected layer because they also realized that fully connected layer tends to generate a lot of parameters. So we also, at the same time, we also moved on to multiple object detection. And then we wanted to build the high performance multiple object detection with very tiny size of the model. So we were inspired by FIRE modules, which was suggested by SqueezeNet. And then we ended up having only 13 megabytes of size for our model. And then we could achieve more than 16 frames per second on the max scale, like 600 by 200, 2200. And then if I explain very briefly about the plot, the rightmost red bar shows the latest model. And then the y-axis showing some performance score based on frame per second, which is the speed and the precision. So we achieved a lot of improvement in the performance, both in speed and precision, compared to the original VGG16, which is shown as a blue here. And then the other three are another model from ours. And next year in ITSWC in 2016, we also did a demonstration of the multiple object detection system, which we had a 2 GPU, two 1080s running on 2 GPUs in real time to detect the objects from the 4 different views. So we had a rear view, front view, and then left and right views. And then these are the sample results that we demonstrated. And then we also collected the data from the Stanford by just driving. And these are detecting cars, bicyclists, and pedestrians. And what's the next? Now we have like very good detector which works fast and which achieved high performance. And then for the ADAS, we wanted to do the risk management. So since we have the localization of the objects, now we can track it. So by tracking each object, we can do the critical risk management, right? Because we can build the trajectory of each object. So we also built the multiple object tracking system, and then we achieved state-of-the-art performance on the KTMOT like a couple months ago. Now we did the publication, and it's going to be presented in the next GTC. And then this final video shows the combination of the multiple object detection that we developed and the tracking system. And then the number shows the ID of each object. So, in my conclusion is, we want to, even though there's a trade-off between the two, we want to achieve both of them, like speed and accuracy. So accuracy, you can keep the accuracy when you use deep neural network, because we all know that deep neural network has been working really well for such kind of task. So to improve the speed, we removed the separate region proposal steps, and also we tried to optimize the network size to maintain very tiny model size to be deployed into the low power devices. So this is how we achieved during until 2016, and then now to have better performance, we are also working on data quantization, model quantization, and etc. So I guess that's it. Thank you.
So we have time for a question. I invite you up to the microphones here.
Thank you. It was a very good presentation. Can you compare it against SSD, which seems to be another good object detector?
Yeah, I was actually predicting this question. So yeah, SSD, single shot detector. It's also does a good job because it's the most recent algorithms, but it still does the RPN stuff. It's more similar approach to the faster DNN. And then we believe that this proposal step of the bounding box, and nowadays, even some people says, oh, there might not be needed for us to have the bounding boxes at all, right? So that's why they're doing some segmentation level too. So we believe that region proposal is really unnecessary for the object detection system. So in sense, SSD are taking slightly different approach than us.
Any more questions? Otherwise, we can thank the speaker again. Thank you.
Thank you very much.